Okay, so let's begin the lecture. Yeah. So the first point says that an object बेटा ना करे क्लास में बातें ठीक है ना जब मैं कह दूं कि stop so you need to stop. Okay. Anyone who wants to talk about something they have to go out first and they can come back. So when I say an object cannot interact with itself, it cannot exert a force on itself. Okay. And why do I say that? Because it's a mathematical object, and by that we mean the particle model. Yeah. So in this initial, you remember this, although for you it's not a second course of physics, but this is one of the very early exposures to physics. So whenever we say an object, we mean that model which will be a particle model. Right? So now if I model myself as an object, yeah, and I do that, so will this be violated? I'm exerting a force on myself. So why will this not, why will this still be okay with this? Because you are not you're actually ignoring one thing. In the last lecture it was clear that by force we mean force acting on the object. So when I'm the object, this is not the force on me. That force has to come from outside. Yeah. So this will be an internal mechanism, and the reason I modeled the whole body as a single particle is because I don't want to know what happens inside. So these things will automatically be. No, whether that is a good model or not is another question, right? You need to know the rules of the game, right? Whether modeling an entire, let's say, planet like Earth as a single particle is a good model or a bad model, that's an entirely separate question. But once you do that, once you do that, then you have to stick to this. So it also happens to, let's say, if you model the Earth and the Sun as a single particle. Yeah, of course, this is a stupid idea, but let's say you do that. So once you do that, then this interaction between the Earth and the Sun will also be ignored because you want to model this as a single particle. Of course, nobody would do that, but you just need to know the rules of the game, right? So same applies to atoms. Yeah, you have atom, you have nucleus, you have electrons. There are forces between them, but once you model an atom as a particle, everything inside is ignored. The only forces that matter is forces on this object, and when I say on this object model is a single particle, and forces by this object on other particles. Yes. No, but that is not. That is. It means that you didn't understand the last lecture, right? He is now referring to the thrust force, right? So the thrust force, you think that the rocket is applying the thrust force on itself. The answer is no, right? The rocket is actually exiting. It's actually giving those high pressure gases to the surrounding, right? And once those gases leave the rocket, they are not part of the rocket anymore. Yeah, so it's not that particle anymore. So now that body of gases, high pressure gases, which I explained in my last lecture, that is now a separate object. So now you have two objects interacting with each other, the rocket and the body of gases, and now they are interacting with each other. Yeah, so the rocket is pushing them, and the gases are actually pushing the rocket back. So every time you want to use Newton's 3 laws of motion, you must remember that you have a particle model in mind. Of course, this doesn't mean that you cannot apply Newton laws to more than one particles, but that is a tricky problem, and then you will have to apply it between any pair. So let's say I have 10 particles. This just to deal with your curiosity, although this is not part of this course. Let's say you have 10 particles, and they're interacting as well, right? And you want to apply Newton's laws to them. What will you do? You will apply Newton's laws to each pair of particles separately. Yeah, and every time you will have to remember this rule, right? The next thing, right? A force exists between two objects, and again, two objects mean two particles, right? Stated otherwise, an object cannot exert a force. So a force requires two objects. Yeah, so it means that an object cannot exert a force at a point if there is no object at that point. Yeah, so when you say that let's say I talk about this object, right? Let's say this is an object, and you say that the earth is exerting a force on it, the force of gravity, right? The moment I remove this object, at that point there can be no force. The earth requires an object to apply a force on it. समझ आ गई बात? So there is no force at a point. There is only force on an object, and that object must be there. So this also means that if you have zero mass, yeah, you can even recall F equals ma. Set m to 0, there is no force, even though the earth is still there. Yeah, ये बात समझ आ गई? So हवा में कोई चीज भी नहीं होगी, ठीक है? Forces can only exist between objects. Period. No more discussion. ठीक है? Next one. Forces do not come out of thin air. Right? You need to identify the source or the agent or whatever, some mechanism. So there is always some source behind every force, and I'm just summarizing the last lecture point by point. And I'm not going to explain these points because this was explained in detail. So let's summarize it, repeat it. A body in motion possesses something. Yeah. So if there is a body in motion, it possesses something which bodies at rest do not have. Of course, what will be your name for that something? Kinetic energy. Why didn't I say that? Because there is another candidate which I already mentioned in my very first lecture, momentum, right? So let's not actually quarrel about that. But what we all agree that a body in motion compared to a body not in motion has something, yeah, which gives it a capability to change things in the world. So it is that ability to change things which is the source of the force. Yeah. So it is the source of the, no matter what you call it, right, is the force it exerts on a body at rest that comes into contact with it. Yeah. So whenever a moving car actually bumps into something and that something is not moving, yeah. So what makes this force actually happen? That ability the object has because of its motion, which you call kinetic energy. Someone else could call it momentum. Yeah. The gravitational force you experience from the earth arises because both you. So this is just to emphasize that two objects are needed. Earth is not enough for the gravitational force. You are also part of that. So both you and earth have mass. So here mass is the source. Yeah? Earth doesn't need to move. You don't need to move to experience that force. In the previous case, motion was required. Motion was the source. But here, mass alone is the source. Yeah? So you just need a body present somewhere. And there is some separation. So mass is not the only thing that is needed, yeah, for gravitational force. There is another thing. The two objects must have a separation. The moment you remove that separation, the force is gone. And what is the other source? Mass. The moment you remove mass, which means remove this object, so you need mass of both objects. Now, can you recall that law, G m1 m2 divided by r square? You need three things. Yeah, masses, separation, and of course this law. Yeah, capital G reminds you that there is a natural law behind it. Yeah. So now there would be no force. This is now the last point is very important, because this bit most of you will remember anyway. There would be no force if you had no mass or you were placed at the center of the earth. I place you at the center of the earth, there can be no force. Why? Because then you become part of the earth, and this will be a single particle, right? So there is no such thing as two particles at a point. Two particles cannot exist at a point. Why? Because they will become a single particle according to your model. This is the important part. So you must not forget the fact that you are using a particle model. That is something which should always be there. Okay? And another example now, electric charge. An electric charge exerts what we call an electric force, right, on another charge, because they both have charges. So charge is one source, right? And they are separated. You need both these things. There would be no force if one of them had no charge or was placed at the center of the other charge. So if you put two protons, yeah, on top of each other, it will be modeled as a single charge with double the value, right? You can only model two protons as two charges when they have a separation. Separation is part of this rule. Yeah? और वहाँ पे भी है k q1 q2 divided by r squared. So the equations you have, you must know the meaning. ये नहीं है कि बस सिर्फ calculation के लिए use करो. Yeah? q1 q2 r, those three things are important. Okay? And both, not just one. So it means that what you remember as the electric field, you remember electric field में क्या होता है? kq divided by r squared. If those of who can remember it, yeah, that is not an electric force. That is the electric field strength. That is an entirely different quantity. Similarly, you can say that okay, Earth has what we call small g, right? Small g, gravitational acceleration. That is not gravitational force. We are talking about the force. So without a second mass in the air, the Earth can give you gravitational acceleration, but it cannot give you force. Force will require an object. So you can have small g without another object, but in order to have m times g, you need that m. The last one. No, sorry, I think there are more as well. The spring force experienced by an object attached to one of its ends. Yeah, this was explained in detail. Is a consequence of the fact that the spring wants to restore to its usual shape. Now the spring. Now this is not motion either. This is just a change of shape. So there are certain things in this world that would always like to restore to their original shape when you want to reshape them. Yeah? So because the spring has been deformed, it has this ability, which you will call elastic energy, right? To come back to it. It's that source which gives, yeah, that was deformed earlier by some agent. So it means that some agent has done something to the spring. A spring that has been deformed possesses, right, what normal springs that has not been deformed, we call them relaxed springs, yeah? Does not have. Yeah? So now you can clearly see that a spring that has been deformed has some capability which other springs which have not been deformed, they don't have it. This thing which you call potential energy or elastic energy or whatever you call it, that is the source of the spring force. Yeah? So you cannot say it comes out of nowhere. No, it has to come from somewhere. And you must know that source. Yeah, because that is the reason, that is what you need when you are identifying forces. The normal force, which you call the reaction force, a book experiences from the table, it rests on, is the vector sum, remember vector sum because force is a vector, of many tiny electric forces arising as a consequence of the book pushing and therefore messing with the interatomic springy bonds at the surface of the table. This is a typing mistake. So now you can realize why I explained the spring force before the normal force, because I want to use that idea of springiness. Yeah. So if you understand how a spring gives you a force, you can now think of the bonds between atoms as tiny springs, right? So there are all these forces, no matter how small they are, but because they are large in number, when they add up, they give you what you call the normal force. So normal force is a vector sum of all those electric forces. Again, you identified the source. The friction force an object experiences as you try to slide. Okay, in these cases, I'm not only telling you the source, I'm also telling you the condition for that to happen. So the book has to press the table. Yeah? If you don't mess with those atomic bonds, they won't do anything. Because there is gravity, the gravity will tend to pull the book down. Yeah? And in so doing, it will mess with those bonds and only then they will react. Similarly, spring, you have to mess with the spring before it can try to restore. So interaction is required, right? An interaction. So you need to understand the interaction and the source, both. The friction force an object experiences as you try to slide it along a a solid. Now, sliding something along a solid. This is the interaction. You are messing with the system, right? So again, you are messing with the bonds. Is the vector sum of many tiny electric forces arising as a consequence? This time, not because you are trying to push anything, but because you are trying to deform it. Yeah, like, yeah, changing a rectangular shape to a parallelogram. Yeah, this is what you want to do. Tiny electric forces arising as a consequence of the object shearing. Shearing is the name we use when you want to actually change the shape of something, and therefore messing with the interatomic springy bonds at the surface. So in both these cases, both the normal force and the friction force, yeah, for them the source is the springy bonds, but the way you interact with them is different. Here you try to compress them, here you try to stretch them, and stretch them sidewise. Not, I mean, you're not pulling anything. The thrust force, yeah, the question you asked, a rocket experiences is the vector sum of the many forces arising as a consequence of the many energetic molecules, because they are high pressure. High pressure, you know, is energetic, right? Of the high pressure exhausted gas molecules bumping into the surface of the rocket. Yeah? So now you will have two bodies. One body has molecules of gas at high pressure. Yeah, so they have high energy. So now you can realize that it cannot be just any gas. It has to be, I mean, that's why you use solid fuel. Yeah? So you convert that solid to gases through some chemical reaction, and in a tiny region of space, you have so many molecules. You know, pressure depends on the number of molecules, yeah, bumping into something, right? Kinetic, if you remember kinetic theory of gases. Okay. Now this point is also important. So these are actually the sources. Exerting more than one external force on an object. So let's say you have an object and you exert more than one forces on the object. Now the physical situation is different from a single force, but mathematically they are equal, right? Just like I'm giving you, you need to understand this. If I say 2 plus 1 equals 3, what do I mean by this equal? The values are same. They have different expression. This is one expression. This expression is just one number. This expression tells me two numbers added together. Two different expressions, but they have the same value. So you need to know what you mean by equality. So when I have an object on which different forces are acting, this is one physical situation. I have the same object on which a single force is acted, which is the vector sum of all those forces. These two situations are mathematically equivalent, which means that if you solve this problem and if you solve that problem, you will get the same solution. Yeah? So this is why I use the name mathematically. Where is it? Yeah, exerting more than one external forces on an object is mathematically equivalent to exerting a net external force, the vector sum of those forces on the same object, right? And this principle, this equivalence is called the principle of superposition. So this is only for you. You can use this principle to solve problems. Yeah? It doesn't mean that they will have the same cost or they will need the same space. They are different situations. So now the next point: an object at rest will remain at rest, or moving object will continue to move in a straight line with constant velocity, right? Although straight line actually, the reason I wrote this straight line in bracket, that when you say constant velocity, that straight line is automatic, but this is only to remind you. Yeah? It's not needed. This is very important. If and only if. You are going to tell me, why can't I simply say if? Why do I say if and only if? But let me complete first. Yeah. The net external force, again, net is always means external, but I'm just reminding you, external. Yeah. So nothing internal going on like that. Yeah. On the object is 0. Now, can you tell me why I strategically explained this fact before this fact? Because without this fact, this is basically the first law of Newton. Yeah, Newton's first law of motion. When people actually see this, They think that no force is acting. No force is acting. Now, this is different from saying that the net force is zero. Net force is zero mean that there are forces, but they cancel each other as a vector sum. This is different from saying that no external force, because no external force, you are not saying net. No external force means that there is nothing interacting with it. That is a very special situation. What Newton is saying is that, okay, there is also one situation, but maybe there are many forces and they just happen to cancel out. You cannot distinguish between these situations. Now, why it matters to you? Imagine, because we are only talking about Newton's law, yeah? I can give you two situations, and in the real world, if I don't follow modeling, it will be different. Let's say I have an object which is being pulled by two, yeah, agents in the opposite direction. After some, of course, it cannot move. It will still follow Newton's law, but after some time, it will just break because some other law will come into play. But if there is no force acting on it at all, nothing will happen to this marker. Two different situations. What Newton is saying is that as far as my laws are concerned, yeah, these two situations are different. But it doesn't mean that they are different in every sense. It's like this. Yeah? These two are mathematically equal, but they are different as far as computation is concerned. Here you get the answer. So I have 3. I don't need any computation. I have my answer in 0 time. But here, I need some physical phenomena to compute this. So how can you tell me these two are the same? They are only the same by their value. Yeah. So the same thing. Yeah. No force acting on it is not physically the same as opposite forces cancelling each other. Only in this sense they are equal. That's why I use the word mathematically equivalent. Right? Is clear ho gaya? Now, this what we just learned is called the Newton's first law of motion, but I need to say something which is mentioned in the book later on, and I want to actually hit it now. This thing valid only in a non-accelerating reference frame. So why this matters? Because when you are saying something that an object at rest will remain at rest, right? This is actually a state of motion. Rest is one of the states of motion, and moving with a constant velocity. Now you must be measuring that velocity, right? So when you are measuring or observing that velocity, you need a reference frame. That velocity has to be relative to something. Now, if that's something, now you remember in the last chapter we studied frames, right? Frame A, frame B, motion of A with respect to B, relative to A, relative to B. So, because observation is involved, the one or the frame in which this velocity is being observed or this rest is being observed, it must not accelerate. Because otherwise this measurement will have an entirely different meaning. Yeah, that is what we mean by inertial frame of reference. And I avoided that term. I'm just calling it non-accelerating for those who don't remember inertial. Yeah. So only in this case this law will be valid, and that's why we call it Newton's first law of motion. So Newton's first law of motion is also called first law of inertia. Why? Because it requires that inertial frame. One, and it is about inertia, because this property of objects to either remain at rest when they are at rest or move with the constant velocity, this is what we normally call inertia. Because the first law is talking about inertia and it is also requiring an inertial frame of reference, we call it the law of inertia. You also call it first law. ये clear हो गया? I want this to be very clear, because many people, your ability to solve problems is actually destroyed when you don't understand this first law. Now, understanding first law doesn't mean just reproducing the words. So many people, they will repeat the words exactly as they are written in the textbook, but they will not know what it means. Yeah? So now you know clearly that we allow forces, multiple forces to exist, but as long as they cancel each other, and by that we mean the vector sum of those forces is 0, right? We are also okay if there is no force. Yeah? So then the object will not change its state of motion. whether it's at rest or whether it's, yeah. So this also means that it is impossible for an object to have acceleration without a force, without a net force. Okay, this is what it means. Yeah? So this last sentence I actually gave you is an indirect definition of force. So you are actually telling how to identify a force. This is another way of identifying a force. One way is to identify those sources, right? Interactions that circle. This is now another way. But that method of free body diagram, drawing a circle, yeah, drawing an imaginary surface, that had no other requirement. You could do that reliably, but that was difficult. Right? You need to know many, yeah, facts. But here, बेटा क्लास में बातें नहीं होगी, ठीक है? बातें नहीं होगी क्लास में. So in this case, this seems to be very easy because all you have to do is to measure the acceleration, and if the acceleration is 0, you can say that the net force is 0. But there is a catch. This is only valid in non-accelerated. But this is what you must remember. Now we can answer the question I posed in the last lecture. You are sitting in a car, right? The car tries to stop, and you move forward, and you bump into the front, actually, yeah, mirror or the windscreen. So what makes you go there? You will think, okay, there is acceleration, so there must be force. So why is that wrong? Because that frame in which you are observing it is non-accelerating. And if you want to know what really happened, ask people outside who are in, and sorry, this is accelerating. The frame in which you are observing inside the car is accelerating. So this is the wrong frame. So Newton's law is not valid there. Yeah? Newton's law is valid when you try to observe the same phenomena, the same motion, the same velocity from outside. And when they observe it, they will never say that someone actually pushed him. What will they say? Inertia. So you are actually following inertia. Why? An object moving will continue to move in a straight line. That's exactly what you are doing. So you are exactly following Newton's law, but this is not a force. Is this clear now? Next one. Now this is an important piece of the next thing. But before that, you must recall what we mean by mass, right? So unfortunately, Newton gave two definitions of mass, and later on he gave a principle where the two are equivalent under certain conditions. But equivalent doesn't mean that they are conceptually the same, right? So one is the gravitational mass. Remember, I just mentioned the law of gravitation a while ago. So how do you write that law? Can you recall? So the force of gravity, and I'm just writing the magnitude, right, equals that constant g, mass of the first object, right? And if you want to write the vector, then you have to write the unit vector as well, but let's not do that. Yeah? I'm only writing the magnitude. Now here, what do you mean by this mass? This mass is conceptually different from the mass you see in the second law of Newton, which is F equals ma. And let me write that as well. I can say F net, right, equals ma. And again, I'm only writing the magnitude. Why are they different? Anyone who has understood that thing, what did I say here when I explained the gravitational force? Read it again. The gravitational force you experience from the earth arises because both you and the earth have. So this is the mass which is the source of gravity. This is called gravitational mass, right? And this depends on how much matter is inside. So the more stuff, the more mass. But this mass is different. conceptually. Of course, under many conditions, they are numerically the same. But I told you numerically the same, 2 plus 1 equals 3, right? So this mass is actually what we otherwise would call inertia. So this is the source of inertia. So first law doesn't say anything about the source of a force. This is not the first law. This tells you where gravitational force comes from. And what is Newton's first law saying? That why objects tend to maintain their state of motion, whether that is rest or whether that is motion. So it gave you actually an indirect definition of two objects, that objects have some property which you can call inertia, yeah, and when there is no force, no external force, and when you measure the state of motion in an inertial frame, then there will be no acceleration. So this m is a measure of inertia. You understand this now? These are two different things. Now, if objects are at rest, yeah, no motion, then these two masses are equivalent. They are equivalent. So it means that Newton chose, because he had to choose units for them. So let's say if you choose kilograms or grams or pounds, whichever units you choose, there is a principle which comes. Actually, that principle, I can even give you a name. It's called the principle of, I think this is the name, reciprocity, but I have to double check it. Yeah. So I mean, even if this name is wrong, there is Newton gave us a principle in which these two masses will be the same. And why it matters? Yeah, because you must have heard that when objects move at speeds closer to the speed of light, what happens to them? Yeah, they get their mass actually increases, right? So it's this mass which increases. That mass doesn't increase. That mass cannot increase because that mass has nothing to do with motion. That mass only depends on the stuff. So the stuff this actually this marker has will not change if it starts moving faster, will it? Yeah? So this means that this mass cannot change, but this mass can change. Why? Because when it gets closer and closer to the speed of light, it will become increasingly difficult to accelerate it further. So the ability of something to oppose acceleration is what we mean by inertia. So it is that mass which will change. But at rest, these two are equivalent. Why did I say that? Because we will now need this mass for the second law. So now you just unlearn this. So you imagine if you don't know this. Yeah, this was only meant to clarify the difference. So now we know, and now you will also recall why we define momentum in a particular way. Yes. The concept is that one is gravitational mass. It quantifies how much stuff do you have in a body. That cannot change regardless of whether you move or you don't move. Whether you move closer to the speed of light or whether you move with the snail's pace. But the other mass, which will appear in Newton's laws of motion, not Newton's laws of gravitation, right? This mass is a measure or a property or a quantity which represents inertia. And inertia is the tendency of an object to resist acceleration. So you can now you can use your common sense that an object which is at rest, it is much easier to accelerate it. You just need to apply force. But imagine that object moving closer to the speed of light. How much energy will you need to accelerate it further? At one point, it will be impossible to accelerate. Infinite mass. Of course, that was the initial concept of mass. Now the concept of mass has changed, but I don't want to go into that. In modern physics, mass has a totally different meaning. It is actually none of these. So modern physicists are not happy with these two concepts. But I'm telling you because now you are not ready at this point to understand that new concept of mass. That I will probably give in a seminar outside this course because it cannot be part of this course. So if you want to know that, you have to talk to the engineering society, fast engineering society, they have to organize a seminar in auditorium, and then I can explain that thing. Yeah? Because I don't want you to be disturbed by that thing. So let's get back to this. So now we have a clear definition of what we mean by inertial. So we will only use inertial mass, right? That inertial mass multiplied by velocity is what we know momentum again. So now it also tells you that inertia is not the only thing, velocity is also another thing. So if an object is moving, how much motion it has, one way of course is kinetic energy, half mv squared, but another way of quantifying that motion is m times v, because a larger mass will have a larger quantity of motion. So you cannot say that two objects moving at the same velocity have the same quantity of motion, because a truck moving at 100 kilometers per hour cannot be the same as a car moving at 100 kilometers per hour. And if you don't trust me, you just try to come in front of it, and then you will see what it means. You will see why momentum matters. So because the air can move very fast, it cannot do anything to you. Why? Because it has a smaller mass, right? So now let's get to so now you imagine an experiment that you keep the mass fixed, the mass of an object fixed, and you change the force, the net force applied on it. And if I now have a plot, and in the book he has proposed an experiment for that. So he's actually recommending that you take some rubber bands, and that rubber band will actually behave like a spring, and the more rubber bands you use, or the longer the rubber band, you can create actually forces. That is actually the spring force. Spring force is the easiest force you can produce in your lab or at home. You just take springs, and you stretch them, and then you leave them, you get a force. So if you take a longer spring, you can have a larger force. So imagine you do that, or maybe you find another way of producing force in a lab. And let's say you have a graph, and you plot that force here, different values, and you measure the acceleration there. But remember, you promised that in so doing, in all these different settings, you're not changing the mass. So you will observe, you can try it, it has been tested many times. You will observe that, and let's say this is not the magnitude, right? If this is magnitude, then I cannot have anything here. Why? I cannot have this line, because the magnitude cannot be negative. If you want to have this line, then you have to change the meaning of this. Imagine you are doing all of this in a single line, and make this the x component of the force. Then that can be positive, and that can be, apply it in this direction, positive, apply it in this direction, negative. If you can do that, then you have this law. And I prefer this, because this you don't need to use the magnitude. But let's keep it like that, as in the book. So in this region, it turns out that A is proportional to F. When I say A is proportional to F, and remember, it is not F, it is F, the magnitude of the net force, right? Now, what is the direction? Can you, based on experience, you must have experienced with acceleration and applied force. Net external force. So if I now ask you, what will be the unit vector of this acceleration, and can you compute that from the unit vector of the net force? What will be the relationship here? Will they be in the same direction or opposite to each other, or at some angle? Same direction. It means that they are literally equal. So when you mention Newton's second law, or when you are developing it, you need to mention both. Because that is only the, remember, many people will try to write something which is not allowed mathematically. What if I do that? Many people write this, but this is mathematically not very good, because proportionality is something which is only applicable to scalars. It is not applicable to vectors. Yeah? You can't have, for example, you cannot say this vector is less than that vector. You can only say the magnitude of this vector. क्योंकि फिर लतीफे होंगे ना. Let's say you have a vector here and a vector here. You will say, okay, this vector is larger than this vector. But what if I do this? Can you say, oh, this vector is still larger because it's pointing to the right, and even though this has a larger magnitude, it's smaller? No, that is stupid. This less than or greater than only applies to scalars, period. Don't apply everything to everything. You need to know where I can apply things. So these two are separate parts of Newton's law. The magnitude of the acceleration observed, for a body modeled as a particle, I'm now saying all those things which are important, is proportional to the magnitude of the net force on that object, provided you keep the mass constant in all these experiments, because this is not one experiment. You imagine all the possible values. In all those experiments, mass has to be kept the same. बात समझ आ गई? Let's do another experiment. अच्छा, यहाँ पे बहुत सारे चीते पता है क्या करेंगे? वो इससे क्या मतलब निकाल लेंगे कि A equals और F equals M है. अभी तो पार्टी शुरू हुई है, ठीक है? So now let's come up with another experiment. This time we will keep the force constant, right? Because you are the one who is producing a force. वहां पे तो आप ये है कि अभी पहले एक ऑब्जेक्ट ले ले, फिर इसके ऊपर दूसरा ऐड कर ले, increase the mass, or decrease the mass. Now keep the force, keep the mass fixed and allow force to change, right? Now in the next experiment, keep the force fixed and change the mass. So let me actually draw that there. And let's say you are doing this experiment, constant force, constant net force. And let's say I'm labeling this with mass and labeling this with acceleration, the magnitude. What will happen here? You can conduct that experiment yourself. It will turn out that because the force has been kept constant, it is actually inversely proportional. Yeah, of course, you can have another line only when you change that force. Just like you can have another line only when you change the mass. As long as the mass is not changed, you will just have a single line with a single slope. So similarly, because if you keep the force constant, the net force, you can only have a single hyperbola. Clear?
So we have straight line there, but we don't have straight line in case.
Because it's inversely proportional. Inversely proportional doesn't mean this. Inversely proportional means I'm now writing the mathematical form, right? When I write the mathematical form, only then you will understand it. So what we learn from this, we will have to write two things similar to that. So A, the magnitude is proportional to 1 over m. If it was proportional like that, it would have been A proportional to m. So here A is proportional, directly proportional. What do you mean by inversely proportional? When it is proportional, when it is directly proportional to the reciprocal of something. Yeah, you know that already. Yeah, like pressure and volume, right? Boyle's law. Yeah? PV is constant, so it means that V is proportional to 1 over P. But this is only for the magnitude. Can you now tell me the other equation? The direction. अब ये चवल नहीं मारना, समझ आ गई? Acceleration will still be in the direction of the force, even though it's a constant. So that same force which you have kept constant, so this equation will not change, because this doesn't care whether force was kept constant or whether mass was kept constant. समझ आ गई? ऑफ कोर्स यहाँ पे हम ये एज्यूम कर रहे हैं कि वो सेम लाइन में है. अगर आप फोर्स की डायरेक्शन चेंज करते रहे, वो गंभीर हो जाएगा. वी वांट टू कीप द एक्सपेरिमेंट Simple. अब बात समझ आ गई है? How do we combine these two laws? We have actually discovered two laws. In both laws, one thing is common. The acceleration is always in the direction of the net applied force, regardless of whether it's constant or whether it's changing. Yeah. So if it let's say if the force changes direction, the acceleration will also change the direction accordingly. The second law is that when force is constant, it is proportional to 1 over m. How do I combine these two? Let's say I have a new experiment where I am allowed to change both f and m independently. What will be the new law? बताएं. You know how to combine two different pieces, yeah? Let me write down here, yeah? Combining this law with that law, yeah? So now listen carefully. A is proportional to you just multiply those two. Multiply 1 over m. Yeah, I can say if a quantity z is proportional to x, and if a quantity z is also proportional to y, the quantity z will be proportional to x times y. This is what you have been doing in math all the time, right? अब मेरा आपसे क्वेश्चन ये है कि व्हाट इज द प्रोपोर्शनैलिटी कांस्टेंट? 1. कैसे आया? खुश? हाँ, बताएं. और दोनों में ये कॉमन है, ठीक है? दिस विल रिमेन द सेम, राइट? How can I turn this into an equation? A equals, I need a constant here. I need some k. And if you are telling me that I don't need that k, so what was it doing there? Let me write the Newton's law of gravity. क्या था वो? ये कोई कबड्डी नहीं है कि आप कह रहे हैं कि उधर नहीं होगा इधर होगा. You can't decide where that I will have a constant of proportionality here and I will not have it because मेरी मर्जी. आपकी मर्जी, आप कौन होता है? So you need to tell me why we have a constant there and not here. और Coulomb's law क्या था? उसमें भी क्या है ना? तो इधर क्या किधर संगी है कि क्या गायब हो गया? अच्छा, यहाँ पे वो जो रट्टा वाली पार्टी है ना, रट्टा वाली पार्टी की अपनी रीजनिंग होती है ना, वो कहता है f is proportional to a and m is constant, so m is the constant proportionality. No, these are two different experiments and I'm combining them. वो तो आप यहाँ पे भी कह सकते हैं ना कि the earth is, let's say this is one mass, right, and this is the earth, right, and the earth is applying a force on them and let's keep it constant. So बस ठीक है, वो constant proportionality मैं उसको इधर ले आता हूँ, गेम में खत्म कर दूँ. ये ड्रामे नहीं चलते, ठीक है? So you need to tell me why. Where is the proportionality of constant of proportionality gone? This is a unique situation which normally doesn't arise, right? Normally, whenever you have a new law, you will have. अब जितने भी laws देखें ना, every time you will have. For example, a common misconception which many of you can have at this point is this. What is momentum? M times. तो can somebody ask कि इसमें भी तो constant of proportionality नहीं है या m है, क्या होगा आपका response? There are two possibilities. Either m is the constant of proportionality, or the constant of proportionality is 1 again here. Yeah. So what will be your answer? That question does not arise here because this is not a law. This is a definition. You are just giving this quantity a new name. Giving name is not a law. Why do we need a constant of proportionality and that capital G, M1, M2? This is what you need to understand, okay? So now we need to answer this question first. F equals G. Why do we need this thing, right? Let's say I remove this, okay? So this equation has a problem. The problem is the two sides have different nature. So mass is a predefined quantity. You know what you mean by mass. You know what you mean by R. So they have units. So it will be kilogram times kilogram divided by meter squared. So if you uh, use that equation as the Newton's law of gravity, there is nothing wrong with that, but that will mean something. That will mean that the unit of force will have to follow that law. That will give you a definition of Newton as well. So what will be the definition of Newton? According to this law, 1 Newton will equal and this is what Newton didn't want. Because Newton was the one who introduced this force for the first time in these two equations, he had the choice. Nobody else had introduced force as a quantity. People were talking about force qualitatively, but not in any formula. So he said that, okay, I will use this equation in such a way that the unit of force will come from this equation. So he chose k is equal to 1 so that Newton is defined as, क्या हो जाएगा इधर? 1 Newton will be so this is the reason. And once you have this, now Newton, the force, the definition of Newton is there. You know what force, how force can be measured. Now here you can't do the same thing again because you cannot have two definitions of Newton. So उसके पास एक चॉइस ये थी कि यहाँ पे G इंट्रोड्यूस करता और दूसरी चॉइस ये थी कि इसको 1 करता, लेकिन फिर वो G यहाँ पे होता. He found it easier to actually do it this way. ये बात समझ आ गई? So these constants are needed for. और अब आप देखें ना, अब आप एक काम करें, अब कूलम्स लॉ को देखें. कूलम्स लॉ वही मसला है, एफ जी और एफ ई फॉर एग्जांपल, के, राइट? If I remove this, then I have to deal with the third definition of Newton. I cannot have three different definitions of Newton. Yeah? So these constants are only there to fix the unit, just like rupees, yeah, dollars, yeah, euros. This is just a conversion, currency conversion. अब समझ आ गई? Now you must, yes. नहीं, वो हम चेंज नहीं कर सकते ना. हाँ, अब आप चेंज कर दे. Let's say that's a good question. That's a very good question. Let's say F equals MA and always write F net, right? Let's say M की जगह मैं लिखता हूँ pound, right? ठीक है? और A की जगह मैं लिखता हूँ foot per second square. I will get a new unit. I cannot call it Newton. I will give it a new name. समझ आ गए? So Newton didn't actually stop that from doing it. He also had a consistent system of units in mind. ठीक है? Yes. क्या चेंज नहीं करेंगे? No. I mean, you as long as you are willing to give that a new name, that's fine. हाँ, अगर आप इसको कोई और नाम देना चाहते हैं फिर मसला होगा. जो कि उसके मतलब if you are the problem, you remember the problem here is that you want to use an existing unit. Remember, if you are willing to have three different units, let's say मैं न्यूटन हूँ, just imagine, ठीक है? और मैं कहता हूँ कि मैं तीन टाइप के न्यूटन डिफाइन करूंगा. या न्यूटन फॉर मोशन, लेट्स से ये एक न्यूटन है और ये है न्यूटन किसके लिए, और एक है इलेक्ट्रिक फोर्सेस के लिए. एंड लेट्स से दैट दिस इज n1, दिस इज n2, दिस इज, then all these three laws will have one as the constant, but that will be stupid. Just because I am saying so doesn't mean that it will make sense. Yeah? But मैं theoretically बता रहा हूँ कि it's possible. तो जो आप suggest कर रहे हैं basically वो ये है कि I'm using pound feet per square and I'm willing to give that a name, but I'll be the only one using that name. Yeah, nobody cares. Yeah. So Newton इसलिए स्पेशल है कि हर कोई न्यूटन यूज करना चाहता है. ठीक है? तो मसला तब होता है जब आप एक एग्जिस्टिंग यूनिट को, अब अगर आप अपना यूनिट चाहते हैं तो यू कैन ऑलवेज चूज द कांस्टेंट ऑफ प्रोपोर्शनैलिटी टू बी 1. समझ आ गई बात? इसकी मैं एग्जांपल दे रहा हूं जस्ट टू क्लोज दिस डिस्कशन. ये जो लॉ है ना, ये क्या आपको इसलिए चाहिए क्योंकि यू वांट टू यूज एसआई सिस्टम, राइट? सो people at that time in Britain didn't like this idea. They said, why should we deal with a strange constant just because of SI? And they hated French because SI was an initiative by the French. So they came up with another, actually Faraday was the culprit, yeah. They came up with another idea. What they did is that they introduced CGS system. You must have remembered this, heard this. And CGS system, this is one. But only in CGS system. But can you force all the people of this world to use CGS system? No. So the reason you have these constants is because you want a consistent system of unit which everyone can benefit from. So units, अब आपको समझ units ने सारी गेम खराब कर दी है. Okay, let's get to the next thing. So remember these two things, yeah? A proportional to F net over M. Unit vector equals unit. I can combine this into this law. Okay? And this is now I can put a vector as well, yeah? So that I don't need to write this separately. So now you can say the acceleration as a vector equals the net force as a vector divided by mass. This is your final statement. इसमें एक गड़बड़ है कि हमने सेट करनी है अभी. And this is, by the way, called the the second law of motion, Newton's second law of motion. इसमें there are some misconceptions when you are using this law, because if you don't know how to use this law, remembering this is not helpful. Now the first thing is that F net is not necessarily a force applied on the object. Yeah, rather it is the net force on it. This is a very common misconception. We think we apply a force and we use this law. No, it has to be the net force. तो अगर आपको net आप याद नहीं है तो आप इसको गलत अप्लाई करेंगे. फिर when computing the vector sum F net on an object, this is the most important part. Do not include forces on other objects, even if those forces are exerted by this object on others. Why? Because this law has to be written for this object when all and the meaning of F net is all the forces on it, not by it. तो वो जो रिएक्शन वाला ड्रामा है वो इधर आपने नहीं लगाना. ठीक है? इसमें या सारे एक्शंस होंगे या सारे रिएक्शंस होंगे. कि अगर आप दूसरी बॉडी की बात कर रहे हैं तो वो सारे रिएक्शंस होंगे. ठीक है? ये नहीं हो सकता कि इसमें एक्शन और रिएक्शन को आप ऐड करें तो नेट फोर्स उसका जीरो हो जाएगा. You will always get a zero because action and reaction will always cancel each other. So you will never be able to use this law. So that is stupid, right? So remember this. Yeah. When computing the vector sum, I'm repeating this so that you remember it. Yeah. Do not include forces on other objects. A common mistake is to include a reaction this object exerts on an agent. That is something you will have to do when you want an equation for that agent as an object, as a new problem, right? Don't mix that thing with this problem. Next one. The acceleration depends on the net force at the present instant, remember. Not on what happened in the past. So there is no memory and there is no lag. So इसका मतलब ये है, अच्छा इसका फिर एक interesting मतलब भी बनता है. What if the sun disappears now? What will happen? If you use this law, what will happen? Or if you use that law? Now, बाकी दफा करो, सिर्फ अपनी बात करो. बाकी मुझे कुछ से लेना देना नहीं है. What will happen to the earth when the sun disappears? According to that law, the centripetal force will disappear, and let's say there is nothing else in the universe. It will just start moving in a straight line immediately. But this is not what will actually happen. Why? Because we are now discussing Newton's laws, and Newton's laws are not correct. Yeah? At this point, we have big names like Einstein. Yeah? Newton, ठीक है, वो बहुत great था, लेकिन इतना भी great नहीं था, ठीक है. So the current theory states that it will take at least 8 minutes for that to happen. No, 8 minutes, because the gravity cannot travel faster than the speed of light. Yeah. So actually, this law and this law, yeah, all these laws are actually approximations, and they must not be relied in modern physics. Modern physics में you will need general theory of relativity, which I am not going to discuss. लेकिन आपके इंजीनियरिंग के प्रॉब्लम्स पे कोई असर नहीं पड़ेगा, ठीक है, क्योंकि ना आप सन पे है और ना सन आपके मतलब आपके जितने भी एक्सपेरिमेंट है उसमें सन कहीं नहीं है. So anything you do in the lab will still be described reasonably well by Newton's law. So you should not worry कि यार ये कोई तबाही आ गई, ठीक है. नहीं ब्रेक नहीं होगा, ठीक है. बाहर जाएं जूस पी के आए, ठीक है. अच्छा, ये क्या हो गया इधर. हाँ, the acceleration depends on the net force at the present instant. तो इसका मतलब है कि ना इस इक्वेशन में टाइम का एलिमेंट है और ना इस इक्वेशन में जो एक्सेलरेशन है वो, इसका मतलब है कि अगर आपने फोर्स चेंज कर दिया तो एक्सेलरेशन भी इमीडिएटली चेंज हो जाएगी. इंक्रीज किया इंक्रीज हो जाएगी. अगर आपने फोर्स जीरो कर दिया एक्सेलरेशन भी जीरो हो जाएगी. ठीक हो गया. लेकिन इससे आप ये मतलब ना निकालें कि बाकी चीजें भी इमीडिएटली चेंज होंगी. फॉर एग्जाम्पल, let's rewrite this law in this form. So instead of writing A equals F by M, bring that M to this side and you will have MA, but MA can be written as the time derivative of momentum, right? Now look at this law. If I change force immediately, let's say I remove the force, what will happen? Will the momentum change to zero immediately? नो, क्योंकि डेरिवेटिव आपने जीरो कर दिया है ना. व्हाट डज इट मीन फॉर द डेरिवेटिव ऑफ समथिंग टू बी जीरो? दैट थिंग विल एक्चुअली टेंड टू बी कांस्टेंट बिकॉज ऑफ इनर्शिया. तो वो थोड़ी देर तक, अनलेस अदर फोर्सेस कम इनटू प्ले, दैट्स व्हाई you cannot bring your car to a stop within no time. You need time. तो अगर ये न्यूटन लॉ ठीक है तो फिर वो तो इमीडिएटली स्टॉप होना चाहिए. तो बेसिकली न्यूटन लॉ वो कह ही नहीं रहा. न्यूटन लॉ कह रहा है कि ए विल स्टॉप इमीडिएटली. तो आप जब ब्रेक्स हटाते हैं तो ए जीरो हो जाता है. इसका मतलब ये नहीं है कि वेलोसिटी भी जीरो हो गई. वेलोसिटी हैज टू फॉलो दिस लॉ. ये भी आप जब ऑन करते फौरन ऑन नहीं होता ये जो प्रोजेक्टर है, और फौरन ऑफ भी नहीं होता. ठीक है. So it means that जब जहां पे भी इस तरह का डेरिवेटिव आता है, so it means that it's better now to rewrite this equation in another form. Let's bring this dt on this side, right? And write this thing as an integral. And you will see what is really happening. यहां पे चेक करें. Bring that t to the right side and integrate both sides. Integrate it from ti to tf. Initial time, final time. So initial momentum subtracted from the, so change in momentum equals the integral of force, net force over time from I to F. Now this tells you the whole story. Even if F net is suddenly made zero, the integral उसमें जो previous values है, अब what है एक constant of integration भी होता है. Yeah? So that those previous values will make sure that this doesn't stop immediately. So actually the summary of all this is that, आपको एक बात है कि हमने चैप्टर 2 में मैंने एक बात बताई थी कि you know displacement is velocity, you need velocity for displacement, right? And you need acceleration for change in velocity, but that will not happen within no time. You need some time before acceleration can convert into a change in velocity. Why? Because acceleration needs to be multiplied by delta t in order to get delta v. So in zero time, no acceleration can be converted to a change in velocity. Similarly, in zero time, no velocity can be converted to displacement. So it's the same here. In zero time, no force can give you a change in momentum. You need time. So when we think of it as a cause and effect, many people think that force is the cause, acceleration is the effect, but that is actually misleading because that hides something. You should actually say that this integral is the cause, not the force. Because force alone cannot do anything without time. So the real cause is not force, but the integral of force. And we have a name for that. Can you recall that? This is called the impulse. The impulse of the force. So the real cause for a change in motion. Now you know why I call it degree of motion. Yeah, momentum is a measure of motion, is a quantity of motion. So the change in momentum, which means the change in motion, if you see this as the effect, so it is the effect of what? Not the effect of force, but the effect of the impulse, right? क्योंकि force cannot change momentum or velocity in zero time. This is what you need to remember. ठीक है? Now let's get back to slides. अभी तक कोई क्वेश्चन ज्यादा पूछ सकते हैं. So this last discussion, actually, the reason why you cannot stop your car instantly, it takes time to bring something to a stop, and that is actually another proof of inertia. Inertia की वजह से हो रहा है ना. और दूसरा क्या है कि you cannot start your car immediately either. From rest you need some time before you. हालांकि एक्सेलरेटर तो आप immediately दबाते हैं ना, लेकिन जो change in velocity है वो कुछ थोड़े टाइम बाद आती है. ठीक है? Even if you are using a sports car, you will still need time. You cannot beat laws of nature. ठीक है? No amount of technology can beat the laws of nature. That is what you need to remember. ये वो एक्सपेरिमेंट से जिसकी मैं बात कर रहा था, ठीक है, वो रबर बैंड्स वाले. Was there any question? Okay, no. अच्छा, वैसे एक बात मैं आपको बताई नहीं है कि what made Newton choose this law for the constant of proportionality as one rather than that law? There was an interesting story about that. आपको याद होगा चैप्टर 1 में ऑर्डर्स ऑफ मैग्नीट्यूड मेंशन थे, याद है आपको? ऑर्डर्स ऑफ, और उसमें ये था कि कैंपस का एवरेज साइज कितना होगा, ठीक है ना. तो वहां पे देयर वाज समथिंग अबाउट एन एप्पल एज वेल, एन एवरेज एप्पल, नॉट टू लार्ज नॉट टू स्मॉल. तो वो आपको याद है वो कितना था? कैन समबडी सी दैट चैप्टर? I can actually go to that now. ठीक है? चैप्टर नहीं, ये नहीं है. इसमें आ जाएगा ना, ऑर्डर्स ऑफ मैग्नीट्यूड. कैन वी सी ऑर्डर्स ऑफ? हाँ, ये है, इधर देखिए. किलोग्राम कितना है एप्पल का? 0.1. अब एक काम करते हैं, लेट्स कैलकुलेट द वेट ऑफ दिस. व्हाट विल बी द वेट ऑफ दिस? ये एवरेज एप्पल है, ठीक है? ठीक है. सो व्हाट इज एम? और मैंने आपको बताया था ऑर्डर्स ऑफ मैग्नीट्यूड में आप एग्जैक्ट वैल्यूज के पीछे नहीं जाते, आप you just use one significant figure. जो 9.8 की जगह आप क्या यूज करेंगे? 10. क्या हो जाएगा ये? अब आपको समझ आ गई? He made sure that apple has 1 Newton of force on it. That would not be possible had he chosen that to be 1. So he wanted us to remember that story. उसके साथ कोई स्टोरी अटैच नहीं थी, ठीक है? ओके. हाँ, तो इसको हम क्या कहते हैं? इसमें रिपीट किया हुआ है, inertial mass. Inertia is a property which is a qualitative thing, but the actual thing is inertial mass. अच्छा, ये वाले जो है ना, ये चीज आप बहुत आराम से इसने बताया हुआ है, ठीक है? So we can actually skip that. Let's get to some of these questions, yeah? Just to make sure that you follow. यहाँ पे क्या लिखा हुआ है? An object on a rope is lowered at a steadily decreasing speed. बल्कि इससे पहले हम एक और कर लेते हैं ना, ये वाला, ये आसान वाला है. An object on a rope is lowered at a constant speed. Which is true, right? The rope tension is greater than the object's weight. Object's weight ऐसे होता है, tension ऊपर होता है, ठीक है? So this is the weight and this is the tension, right? So is this true? Why not? क्योंकि अगर ये ग्रेटर है तो फिर नेट फोर्स जीरो नहीं होगा, और जब नेट फोर्स जीरो नहीं होगा तो स्टेडी नहीं हो सकता, क्योंकि डायरेक्शन चेंज नहीं हो रही है ना, वेलोसिटी भी चेंज नहीं हो रही है. सो दिस विल बी अ वायलेशन ऑफ द फर्स्ट न्यूटन्स फर्स्ट लॉ. ठीक है. नेक्स्ट वन, द रोप टेंशन इक्वल्स द ऑब्जेक्ट्स वेट. ठीक है. अच्छा, वैसे एक बात मैं बता दूं, I'm allowing these types of answer, but if I want to be really precise, then there is an issue here. उसकी वजह ये है कि if you think of these as forces, then there is a problem. Why? Because these two forces are opposite in direction. They cannot be equal. So I'm not the one writing these MCQs. If I'm writing this, I will make sure that I write the magnitude. Yeah? The magnitudes are equal. Directions are opposite. ठीक है. So if you see any MCQs and exams, you need to be prepared for that extra language, yeah, because I want to make sure that you know what you are doing. रट्टे की गुंजाइश नहीं है. या बिल्कुल. अच्छा, यहाँ पे सो ये ठीक है, ये वाला सही है. ठीक है. और ये वाला, द रोप टेंशन इज लेस देन द ऑब्जेक्ट्स वेट. अच्छा, अब अगर ये होता तो, अच्छा अगर ये होता तो क्या होता इधर? नहीं, इसका मोशन कैसे होता? मे बी इट हेल्प्स यू इन द नेक्स्ट क्वेश्चन. यहां मैं ये बताना चाहता हूं कि जस्ट गेटिंग द राइट आंसर इज नॉट इनफ. यू नीड टू लुक एट एवरीथिंग सो दैट it can guide you in the next question. Yeah. So this would mean that this is accelerating downwards, and this would mean that this is decelerating. It must be, so this must be speeding up downwards, this must be slowing down, yeah, when it goes downward, and it is only in this case that it will be steady. Last one क्या है? The rope tension can't be compared to the object's weight. अब ये यहां पे ठीक है क्योंकि इसका मतलब मैग्नीट्यूड है, लेकिन अगर इसका वही मतलब ले ले जो मैंने भी थोड़ी देर पहले लिया था तो फिर ये ठीक है, क्योंकि यू कैनॉट कंपेयर वन वेक्टर विद अनदर वेक्टर. ठीक है, अनलेस यू टर्न देम इनटू मैग्नीट्यूड्स. और ये इसका दूसरा क्वेश्चन है, स्टेडीली डिक्रीजिंग स्पीड. तो आप उसी क्वेश्चन से गाइडेंस ले लें. और कौन सा ठीक है इधर? दिस वन, राइट. इनर्शियल रेफरेंस फ्रेम ऑलरेडी मैं एक्सप्लेन कर चुका हूं. ठीक है, कि द फ्रेम इन विच यू आर मेजरिंग मोशन मस्ट बी इनर्शियल इफ यू वांट न्यूटन्स लॉज टू बी वैलिड, अदरवाइज न्यूटन लॉ आप अप्लाई नहीं कर सकते. ये इसने दूसरी एग्जांपल दी है कि आप एयरप्लेन में आप देख रहे हैं कि जैसी वो टेक ऑफ या जो भी है, सो यू सी दैट एनीथिंग लाइंग ऑन द फ्लोर विल स्टार्ट एक्चुअली गोइंग बैकवर्ड, देयर इज नो फोर्स ऑन इट. ठीक है, वो इनर्शिया की वजह से जा रहा है. सो एक्सेलरेटिंग रेफरेंस फ्रेम्स आर नॉट इनर्शियल रेफरेंस फ्रेम्स, एंड इन दीज फ्रेम्स यू कैनॉट अप्लाई न्यूटन्स लॉज. और ये भी, ये वो अर्थ वाली एग्जांपल मैंने दी, इफ द सन डिसअपीयर्स, या सो लेट्स से यू हैव समथिंग इन दिस, या एंड यू सडनली ब्रेक इट एट वन पॉइंट, इट हैज टू गो स्ट्रेट, क्योंकि सर्कुलर जो मोशन है वो एक्सेलरेशन के बगैर पॉसिबल नहीं है, राइट. अच्छा, आपसे मेरा एक दूसरा क्वेश्चन है. अगर आप न्यूटन्स की फर्स्ट लॉ को देखें, सो इफ देयर इज नो एक्सटर्नल फोर्स, राइट, सो द ओनली ईदर इट विल बी मोशनलेस और द मोशन हैज टू बी इन स्ट्रेट लाइन एट कांस्टेंट स्पीड. तो ये जो अर्थ की, ये तो समझ आ जाती है ना, सन के अराउंड जो ऑर्बिट कर रहा है, दैट इज बिकॉज ऑफ ग्रेविटी। या वो तो आप कह सकते हैं कि वो चूंकि सन का फोर्स है तो इसलिए वो क्या है, ये स्पिन किस खुशी में कर रहा है? स्पिन के लिए तो सन की ग्रेविटी नहीं चाहिए ना। So if that sun disappears, although it will leave this orbit, but it will still keep spinning. Spinning कहीं नहीं जा रही। तो स्पिनिंग कैसे हो रही है? स्पिनिंग तो फर्स्ट लॉ ऑफ न्यूटन के अगेंस्ट नहीं होनी चाहिए। आप मिस कर रहे हैं पॉइंट को। न्यूटन लॉ इज अबाउट अ पार्टिकल एंड अ पार्टिकल कैन नॉट स्पिन। For that you need to learn modern physics. Spin is a fundamentally different concept which is not in Newton had no idea of a spin क्योंकि he was only dealing with particles. ठीक है, तो स्पिन के लिए आपको क्वांटम मैकेनिक्स में जाना पड़ेगा। यस, बहुत सारे लतीफे आपको इंटरनेट पर मिल जाएंगे अगर आप सर्च करें, क्योंकि दे डोंट नो कि स्पिन इज समथिंग व्हिच इज नॉट इवन इंक्लूडेड इन न्यूटन्स लॉज। ठीक है, ओके, ये वाला बता दो। An elevator suspended by a cable, yeah, you have seen this in the other blocks, speeds up as it moves upward from the ground floor. Speeds up. ठीक है, identify the forces and draw a free body diagram of the elevator. कौन से forces होंगे? टेंशन इन द केबल हो जाएगा, ग्रेविटी और नहीं, वो ग्रेविटी तो डायग्राम ऑफ फ्री बॉडी डायग्राम ऑफ द एलिवेटर है ना, तो ग्रेविटी आ जाएगी ना। अंदर लोगों का क्या करेंगे? नो, देयर विल बी, यही तो मसला है, यू हैव टू मॉडल एवरीथिंग एज अ सिंगल ऑब्जेक्ट। ये ड्रामे नहीं करेंगे आप, ठीक है? अच्छा, वो मसला आपका नहीं है, मसला नहीं, न्यूटन ने हमें फ्रेमवर्क नहीं दिया ना, जो फ्रेमवर्क उसने दिया है हम वही करेंगे। ठीक है, लुच एक्स्ट्रा लुच हमने नहीं तलना उसमें। ये देखें, ठीक है, ये ग्रेविटी है, ये टेंशन है, और नेट फोर्स हमें पता है अपवर्ड है। क्यों? क्योंकि स्पीडिंग अप। अच्छा, मेक श्योर दैट इन दिस डायग्राम द डॉट इज एट द एलिवेटर और विच एवर ऑब्जेक्ट यू आर स्टडीइंग इट, the arrows must be such that each force has a tail at the object, and because net force is another thing which is a mathematical concept, F net is not a real force because it is something you calculated. Make sure you indicate that outside the diagram. इसको यहां ना डालें वरना ये कैंसिल हो जाएगी, जीरो हो जाएगी, फिर समझ आ गई? यहां पे रियल फोर्स होंगी। दिस इज नॉट अ रियल फोर्स, दिस इज एक्चुअली अ मैथमेटिकल फोर्स यू कंप्यूटेड। समझ आ गई? तो ये दोनों आपको ये दे रहे, दिस इज इक्विवेलेंट टू दीस टू रियल फोर्सेस। ये है, इसकी मिसाल ऐसे है ना कि मैं इसकी एग्जांपल दे रहा हूं। सो लेट्स से you are comparing masses of two objects with a spring with a balance, yeah, not with a spring balance but with that old fashioned balance. So you have an object here, an object here, and they are in equilibrium. So what is the net mass? Zero. But that doesn't mean that there is no object. Yeah? There are two objects. The net mass is zero, right? The net weight is zero. It is different from those two actually slots being empty. So empty is a different thing. So मैं बताना चाह रहा हूं कि when you say zero and you say 0 equals 2 minus 2, these are numerically equal, but this is one concept where you have nothing. And here you have two things cancelling each other. These two sides are only equal numerically. ठीक है, इधर बताएं जरा। A ball hanging from the ceiling by a string is pulled back, ठीक है, and released. Which is the correct free body diagram just after it released? So आप इसको छोड़ लेते हैं, तो आप बताएं कौन सा होगा। अब इसमें चूंकि टेंशन होगा ना, तो ये नहीं हो सकता क्योंकि टेंशन मिसिंग है। So it has to be one of these three, one of these four, right? और फिर उसके बाद ये वाला, ठीक है. अच्छा ये नहीं, यहाँ पे मसला पता है क्या है? यहाँ पे आपने क्या किया हुआ, ये फोर्स कहाँ से आ रहा है? तो आप नेट फोर्स लगा रहे हैं ना. तो नेट फोर्स मैंने बताया है कि वो इधर नहीं लगाना, वो अपने साइड पे लगाना. समझ आ गई? तो अगर ये ठीक, अगर इसने इसको ठीक कहा भी है तो खैर अव्वल तो है इसका नेट ही है नहीं ना, नेट का ये नहीं है, ठीक है. और अगर लेट्स से इसको ये ठीक करता भी है सो ही इज फॉरगेटिंग दैट कन्वेंशन कि नेट फोर्स आपने इस डायग्राम में नहीं लगाना, वो अलग से होता है. ठीक, यस, ठीक है. उम्मीद लाज रख दी उसने. अच्छा, आप फोर्स नहीं कर रहे, आपने उसको छोड़ दिया सिर्फ. यू पुल्ड इट एंड देन रिलीज्ड इट. एंड इवन इफ यू गिव इट अ फोर्स देन यू विल बी लूजिंग कांटेक्ट. मैंने क्रिकेट वाला, यू कैन ओनली गिव इट इनिशियल वेलोसिटी. वो फोर्स फिर भी यहां जीरो होगा. फोर्स के लिए कांटेक्ट जरूरी है, कांटेक्ट तो आपका होगा नहीं ना. समझ आ गई? सो आप जैसे उस किसी चीज को किक करते हैं, सो इट इज ओनली ड्यूरिंग दैट टाइम दैट यू आर इंटरेक्टिंग विद इट. आफ्टर दैट नो इंटरेक्शन. ठीक है. एंड देयर इज नो सच थिंग एज अ फोर्स ऑफ मोशन, राइट. ये आप नहीं कह सकते कि जो कि मूव कर रहा है सो देयर इज अ फोर्स, क्योंकि हॉकी नहीं खेल रहे हम. ठीक है. ये वाले आप खुद कर लेंगे कि हम डिस्कस कर चुके हैं काफी दफा. ठीक है. अच्छा, ये जो आपका है ना, ये जो मैं बता रहा था कि द फोर्स, द एक्सेलरेशन विल be a consequence of the net force at the present instant. This is so important that people call it Newton's zeroth law, although he didn't say anything like that, but just to remember it, it's Newton's zeroth law. तो अब हम एक काम करते हैं ना, ये इस चैप्टर का let's actually so now I suppose something, that once you know the real meaning of these two laws, right, the first law and the second law, and if you remember all these different facts, you can easily apply it to any problem, right. इसमें एक चीज अभी रहती है और वो है action reaction, but I think I have explained it, although it was not part of this chapter, but I explained it as part of the discussion, because I mean, if I was living at that time of Newton, I would have asked him that your first law should be your third law. Why? Because you cannot have a force without two objects. So the very concept of force requires two objects. How can you have that as a third law? That should be the first law. समझ आ गई? क्योंकि मतलब आपको ये इंप्रेशन मिल रहा है कि जैसे फोर्स, नो, if force requires two objects, then action reaction is the very first word you have to mention. ठीक है ना? And then you call it force. But मैं तो था नहीं, ठीक है, वो करने दी जिसने भी उसने किया है. But मैं वो करूंगा जब मैं यहाँ कर सकता हूँ. Okay, let's. I don't need the board now. ठीक है? So I need something. Now we will start from something, and I'll start. Can we turn this off? Who can turn this off? Because I need this. Yes, please do that. Okay. So let's now. I need to actually make sure that this time is actually effectively utilized. So remember that I told you that this. Let me first test your understanding so far. Why do we prefer to write it in this way and not in this way? Which of these two is more revealing? The second one. Why? Because it establishes the cause and effect. You typically write the cause on the right side and the effect on the left side. So this is the first thing you need to note. I was then not happy with this one either, because this gives you the impression that the force which you call cause, although A is the consequence and that can happen instantly, but the real change in motion cannot happen instantly. So in this form, the law is not very useful. So a more useful law will be to bring this M there and then rewrite this as, and then you say, so here it tells you that a force as a cause can change momentum or velocity, right? Here you even allow mass to change. So change of momentum is a better word, because it can capture those tankers, yeah, which lose water as they go. So mass can change. This allows you to change mass. Okay? You can even apply it to rockets. How will you apply this to rocket? If you model the rocket and the gas as a single object. Okay? But let's not get into that. So I was not happy with this either. Why? Because anyone who does not understand the concept of derivative will still get the impression that this can happen instantly. So a better version is to bring this dt on this side, right? And now the final form, which is f net, right, dt, and let's say this is ti, the initial time, tf, the final time. So now you have a quantity which is the aggregated some aggregation of the force. Force at one time cannot do anything, but force applied for a time interval can do something, and that's why we need a new name for this, right? अच्छा, ये यहाँ पे भी जरूरी है कि even if you look at that, although there is an equal sign, the two sides have different meaning. Many people misunderstand that this is a definition of force. You're not defining force here. Force has been defined in the first law. So the definition of force is qualitative, right? You can use this equation for measuring force, but these two are different concepts. This is the external force, net force, as a cause, and you have to think of this as an effect. And cause and effect are never the same. They are conceptually separate things. So same is here. This integral of the force is the cause. Why? Because it has force, which is the cause, and you're just integrating it over time. What is the effect of this on that side? Change in. So this change in momentum on the left side is the effect. This is the effect, and this is the cause. और इस cause को हम क्या कहते हैं? Impulse. ठीक है? अब यहां पे एक काम करते हैं. You may think that the idea of a force is a must, because this simplifies our language. But now I'll give you two examples, right? Let's say कि मेरे पास दो ऑब्जेक्ट्स हैं, M1 और M2. ठीक है? लेट्स से ये M1 और ये M2 है, और इसकी वेलोसिटी क्या है? V1 और इसकी ठीक है? और these are the velocity before they can have any impact. So because I want to distinguish between what happens before and what happens after, so let me attach labels. So I for the initial, right? And when they have an impact, क्या हो जाएगा? Now this is actually before, ठीक है? और अब मैं लिख रहा हूं after. तो आफ्टर में क्या हो जाएगा? ठीक है, बल्कि इसको मैं उसी तरह लिख देता हूं. So let's say this is V2F and this is V2I. So when they were interacting, अब यहां पे जो डिफरेंट व्यू चाहिए ना, आई नीड फ्रॉम यू अ डिफरेंट व्यू. डिफरेंट व्यू ये है कि how can we remove force from this whole picture, right? uh, if you model this as a single object, I'm not going to give you all the computations, but I just give you a strategy. Let's say you want to repeat this at home. So let's say you choose one of this one as the object of your interest, then this will be the agent, right? And you will be writing your equation of motion for this object, right? So change of momentum for this object as a consequence of the force by that object when they encounter, and you write your equations, right? And you can repeat the same thing for this as well. Yeah. So now think of this as the agent, even though it is slower and it is faster, but in the interaction you can choose this as to be your object and choose the other one. Object means subject. Choose the other one as the agent. So you can write two independent equations. You combine them algebraically, and you remove the force. Why? Because the force, one of them will be action, the other will be, and because they are equal in magnitude and opposite direction, you imagine going back to school, you have two equations with a common F net between it, only with a negative sign. So you can eliminate that force from those two equations. Can you imagine that? So just to repeat my story, I have one equation for this based on Newton laws, one equation for this. They both will have F net as the external force, but because action and reaction are the same, I can actually combine those two equations and that F net will disappear because it will have a minus sign. So at the end, I will get something which will have no force in it. So it means that as far as this interaction is concerned, I don't even need to talk about force, but I can express this situation in a new language. Just like when you have a transaction with someone in business, one of you gains from that transaction and the other one loses. Yeah, gain, loss. So why not think of it this way? These objects interacted, and as a consequence, one of them lost something and the other one gained something. And what is that thing? Momentum. Momentum. No, don't say velocity. Why? Because you eliminated force, and force, the integral of the force was a change in momentum, not a change in velocity. So you cannot say this lost velocity and this gained velocity. No, you want to equate those two things as well. So this lost momentum and this gained momentum. नहीं कांस्टेंट कैसे है? इधर m1 है, इधर m2 है. समझ आ गई? तो मास कांस्टेंट नहीं है. तभी यहाँ पे you have to think of this as a single, as a closed system. So in a closed system, the momentum cannot change. But if you think of them as different objects, you can say, okay, forget about force. So now we can say this is the main idea about the law. You must remember that law of conservation of momentum. It comes from Newton's third law. It's not a new concept. It's a consequence. क्योंकि और आप अगर आप चाहे आप रिपीट कर सकते हैं. आप इसके लिए लिखे और इसमें जो F होगा और उसमें जो F होगा उसमें नेगेटिव होगा. आप इक्वेट करें इधर मोमेंटम. Just do the algebra. ठीक है ना? So one of my friends, he didn't like algebra, so he would say bloody algebra. ठीक है? So do the bloody algebra and you will get actually the law of conservation of momentum. But this raises another question. This now raises another question. And let me write this again. ठीक है? So force now this thing is this thing will need some creativity on your part. Yeah. I want to ask you something. here my claim is that force as an abstraction of interaction cannot do anything in no time. That's why I need to integrate this force over time, right? But is this the only aspect you need to be aware of? Force also needs some other thing. It also needs to move. A force can do nothing if you restrict it to a single point. If I want to move something, that force has to move as well. So it means that dt is not the only thing that is necessary. dx is also important. समझ आ गई? अगर मैं फोर्स को इधर ही रख दूं और if I don't allow that agent to move, that agent cannot do anything. ठीक है? अब आप कह सकते हैं कि सन तो उधर है, वो तो कहीं नहीं आ रहा, बट दैट इंटरेक्शन विद द अर्थ वो उसको छोड़ नहीं रहा ना. ठीक है ना? द फोर्स इज एक्चुअली फॉलोइंग इट बिकॉज इट्स अ लॉन्ग रेंज फोर्स, सो इट्स एवरीवेयर. सो दैट फोर्स इज एक्चुअली moving. So now let me do something like this. Let's try to integrate this force not over time but over displacement. And this time let me keep things simple, right? Instead of dealing with vectors, let's stick to one dimension to keep our life easy. So in one dimension, rather than talking about force as a vector, I'll only talk about the component of that force along x-axis. तो यहाँ पे क्या हो जाएगा? So now I'm integrating the component of force along the x-axis, and I'm integrating it with respect to axis. And let's use the same language: initial position and final position. And let's see what do we get out of this. You will get something amazing. ठीक है? So what can you do so far? यहाँ पे fx के लिए आप न्यूटन का लॉ अप्लाई करोगे तो क्या होगा? And let's say this is the only force, this is the net external force, nothing else is going on. Yeah? तो ये क्या हो जाएगा? m. You are applying this on m. ये वही m है जिसके ऊपर आपने ये लॉ अप्लाई किया हुआ है. ठीक है? So that was one way of looking at the problem. Now you are looking at that same problem in a, or let's to keep it consistent, I'll also use the same fx there as well, because the same problem viewed from two different perspectives, right? तो क्या हो जाएगा? max or dx. So far so good. Yeah. What else can I do? Let me change this ax. You know it, a better way of writing this ax was dv by dt, right? तो क्या हो जाएगा? dv by dt. And how about combining these two? Because you can write dx as v dt, that dt will cancel out. So what do I get at the end? I'll get dv here and I'll get v here, vx, sorry, v. So dx by dt is vx. So what do I get at the end? vx dv. You can try this at home. There is no fancy, nothing fancy, no rocket science, just pure algebra. Okay? But these limits have to change, you know, change of variable. So now I can no longer say xi and xf. What will I say? Because now I'm integrating with respect to the component of the velocity. So it will be vi, vf. Yeah? Humble algebra. There is no fancy stuff. अब बताए इससे मुझे क्या देगा? You know how to integrate this. m कांस्टेंट है, उसको बाहर ले आए. ठीक है? इसका क्या है? मल्टीप्लाई बाय 2 डिवाइड बाय 2. 2x किसका डेरिवेटिव है? v स्क्वायर्ड का. एंटी डेरिवेटिव vf स्क्वायर्ड माइनस vi स्क्वायर्ड. तो हाफ mvf स्क्वायर्ड हाफ Same problem, two angles. So when you look at force as if it were acting over a time interval, you get a change in momentum. But the same force, you just change your view. You can also view this as if this force is acting over some displacement, because force, and you don't allow it to move, it cannot do anything. Yeah, take it up. The gases have to expand if the car has to move, right? So that this is another way. So this is one overall effect, overall accumulation. So इसको हम क्या कह रहे थे? इसका नाम क्या था? We need a new name for this now. No. मैं बता रहा था कि ये दोनों इक्वल का मतलब ये नहीं कि कंसेप्चुअली सेम है. This is the impulse, this is the change of momentum. They are only numerically the same. This is the cause, this is the effect. आप इसको चेंज ऑफ मोमेंटम नहीं कह सकते और ना आप इसको इंपल्स कह सकते हैं just because there is an equal sign. No. Only this is the impulse, क्योंकि वो कॉज है, ये इफेक्ट है, तो क्या होगा? तो आप इन दोनों में से अपनी मर्जी से नाम नहीं दे सकते. This is something which you constructed from the force. This is the cause. That is the effect. तो इसको वर्क कहते हैं. Work is the integral of force over displacement. Impulse is the integral of force over time interval. दोनों में से कौन सा सिंपल है अगर मैं आपसे पूछूं, without getting to the rest of the math? No. That is a vector and this is a scalar. A scalar is just one number. You are telling me that a vector is easier to deal with than a scalar. अब आप पता ही क्यों कह रहे हैं? क्योंकि आपने वो पहले पढ़ा हुआ है, पहले और दूसरी से निकल रहा है, ठीक है ना? Vector will always be complicated. Scalar will always be. That is a vector too. And this is a scalar. So work will give you change of kinetic. So now you automatically have a new name for it. There is no way, you must give it a name. There is no other way. And there is no, you don't need to memorize it. It has to be this way. There is no other way. And this has to be this way. So even if you don't know anything about momentum had to be, someone had to define it, because otherwise you can't do physics. So repeat this. Impulse will give you a change of momentum. Work will give you a change of kinetic energy. Now, one last thing. If let me pronounce this, what will you say? Mass times velocity, right? So how will you pronounce this? Half times mass times? बताएं आप. Speed squared. You cannot have velocity squared because velocity is a vector, and you cannot take the square of a vector. Yeah? ठीक है? तो जब मैं यहाँ पे VF लगा रहा हूँ, इसके साथ अगर x लगा भी दिए, x कंपोनेंट का स्क्वायर आप ले सकते हैं, लेकिन वेक्टर का स्क्वायर नहीं आप नहीं ले सकते. ठीक है? सो काइनेटिक एनर्जी, अब आपको समझ आएगी काइनेटिक एनर्जी. अब आप मैं क्यों कह रहा था कि दे आर बोथ मेजर्स ऑफ मोशन. इसने भी मोशन को चेंज किया, इसने भी मोशन को चेंज किया. अच्छा, अब आपको एक और बताओ, यहां पे आपको लगेगा कि मैंने कोई बहुत फैंसी मैथमेटिक्स यहां अप्लाई किया है ना. You already know this equation in another way. If you wanted, you could avoid this integration and you just recall the third law of motion by Galileo. वो क्या था? Vf squared. बताएं जरा. Minus Vi squared equals और ये S ना करें ना, डेल्टा एक्स हो गया, या आप इसको कह दें एक्स आई, एक्स इफ माइनस एक्स आई. ठीक है? या आप ये भी कह सकते हैं कि इसको आप डेल्टा एक्स कर दें. ठीक, डेल्टा एक्स. लेकिन वहां पे एक्स कांस्टेंट है, यहां पे कांस्टेंट नहीं है, इसलिए आपको इंटीग्रल चाहिए. वहां पे एक्स क्या था? कांस्टेंट था. तब आप दोनों को मल्टीप्लाई करें एम से और फिर हाफ से कर दें, यू गेट दैट थिंग. You knew it. Yeah, we didn't have enough imaginative skills. हाँ, सिर्फ ये फर्क है कि वो ए कांस्टेंट, यहाँ पे ए कांस्टेंट नहीं है. You don't need, क्योंकि ए कांस्टेंट मीन एफ कांस्टेंट, सो वी डोंट रिक्वायर एफ टू बी कांस्टेंट. ठीक है. तो अब इससे एक चीज क्लियर हो गई कि दोज ऑफ यू हु वर सेइंग दैट energy and work are the same, no, they are not the same. This is energy, this is work. They only have the same units. They are different concepts. Why am I saying that? अब ये next concept है, बहुत जरूरी है. And from the very start of this course, I have been emphasizing that you need to know what you are dealing with. So when you model something as a particle, you declare that is my object of interest. So any property has to belong to that object. Now think about these two properties. Momentum, see momentum as a property. Momentum belongs to that object, right? Kinetic energy belongs to that. It's a property of that object. Can you say that object has the impulse? No, because impulse comes from outside. It belongs to the interaction. Work belongs to the interaction. You cannot say this object has this much work. Work cannot be a property of an object. Why? Because work requires interaction, and interaction is only between two objects. तब अगर आपसे मैं लास्ट क्वेश्चन पूछ लूं, कितना टाइम है हमारे पास? हाँ, नहीं बस this is now the last question. Let me, I need something which doesn't break if I throw it. ये वाला ठीक है. मोबाइल अच्छा रहेगा अगर वो मेरे पास रहे तो ठीक है. अच्छा, अब एक बात बताइए, इधर है, ठीक है. अब इसकी काइनेटिक एनर्जी कितनी है? 0 है, ठीक है. और मैं अभी इसको मूव कर रहा हूं, तो अब इसकी काइनेटिक एनर्जी क्या है? 0 नहीं है, ठीक है. एंड यू कैन सी कि m भी इसका अपना है, और तो आई कैन सेफली से कि काइनेटिक एनर्जी इसकी अपनी है, ठीक है. अब ये इधर से इधर आ गया, क्या चीज इसकी इंक्रीज हुई है? अब तो स्टॉप हो रहा है ना. पोटेंशियल एनर्जी आप कह रहे हैं किसकी है? इसकी. अब मुझे आपने इसका फॉर्मूला बताना है, वो क्या है? So when I listen carefully, when I was saying that kinetic energy is a property of this object, I was justified because m was its own and v was its own. उसमें एक एक को हमने लिस्ट करना है. m इसका अपना है, हाइट इसके अपना किस खुशी में है? हाइट इसका है. ये दोनों चीजों का इससे कोई तल्लक नहीं है. अब मैं पंजाबी वाला वर्जन बता रहा हूं, क्योंकि जो चस तल्लक में है वो ताल्लुक में नहीं है, ठीक है. जी और एच इसके नहीं है. जी और एच किसके है? अब बताओ. वो अर्थ की भी नहीं है. नहीं सॉरी, जी अर्थ का है, सॉरी, मैं थोड़ा सा ज्यादा आगे चला गया ना. शबाज शरीफ मोड है ना ये, और शुक्र है मेरा भी कुछ थोड़ा नहीं है ना. तो जी तो अर्थ का हो गया, एच दोनों का है, एच दोनों के दरमियान. तो एक बात तो क्लियर है कि आइंदा से मेरे सामने कोई ये ना कहे कि ये इसकी पोटेंशियल एनर्जी है. समझ आ गई बात? पोटेंशियल एनर्जी दोनों की है, क्योंकि H दो के दरमियान है. समझ आ गई बात? पोटेंशियल एनर्जी इज द एनर्जी ऑफ इंटरेक्शन. इंटरेक्शन रिक्वायर्स टू ऑब्जेक्ट्स, पीरियड. इसका अगला वर्जन बताएं, अगला वर्जन. टाइम खत्म हो गया, ठीक है.